Unit 5 is called SOAP. In this unit, we will study the types of bonds and the compounds that they form, as well as their properties. We will learn how to draw molecules. We will learn then how to look at a drawn molecule and predict a three-dimensional shape that molecule will take in space. And then in part B, we will look at predicting the polarity of molecules based on this three-dimensional shape. And then we will look at intermolecular forces, the forces between the molecules and how they affect the properties of the substances. In section 5.1, we'll talk about the types of bonds. So why do atoms bond? Well, we've determined that atoms are most stable when their outermost shell of electrons is full. This means that they must have 8 electrons in their outer shell, in their valence shell. Atoms will bond to other atoms to fulfill this requirement. While most atoms desire 8 electrons in their outer shell, there are some, such as hydrogen and helium, that only want 2 electrons in their outer shell. We call this the duet rule. Remember that valence electrons are the outermost electrons in the highest energy level. If we use the periodic table, the group number next to the letter A of the representative elements, those are the towers on the periodic table, represent the valence number. This is a good shortcut to acquiring that magic number. As an example, remember that group 1A will form 1 valence electron, whereas elements in group 5A form 5 valence electrons, and elements in group 8A can form 8 valence electrons, keeping in mind that helium only will form 2. Remember that Lewis dot diagrams are a great way to show the valence electrons. Remember, atoms only have 4 orbitals available to hold electrons, 1s and 3p. That means there are 4 places to put the electrons. Since oxygen has 6 valence electrons, if we were to draw that Lewis dot diagram, we would go ahead and put a dot on each side first to represent the s and the 3p orbitals, and then we would go back to make the 5th and the 6th electron. Here's a quick snapshot of some other Lewis dot diagrams. So a bond is like glue holding the atoms together, but really that glue is forces of attraction between the valence electrons of differing atoms. And one of the reasons why we find more compounds than single atoms is because when the atoms come together, they lower their potential energy, and that creates stability. So there are 3 types of bonding: ionic, covalent, and metallic. The first type of bonding is called ionic bonding, and it's between a metal and a nonmetal. We know that metals tend to lose their electrons and become positively charged, forming cations, whereas our nonmetals tend to gain electrons. They become negatively charged, anions. When the metal approaches the nonmetal, there is a transfer of electrons, and the charged particles are electrostatically attracted to one another, forming the ionic bond. Take a look at this picture, and you can see sodium's Bohr model with 1 valence electron in the outer shell. We know sodium wants to lose that 1 valence electron, and so it will become positively charged when it is transferred over to the chlorine. Notice that the chlorine has 7 valence electrons in its outer shell of the Bohr model, and we know that when it gains that 1 electron that sodium is going to give it, it will become negatively charged. And then that electrostatic attraction between the positive and negative charges will bring the Na and the Cl together to make sodium chloride. One of the ways that we can represent this is our Lewis dot diagrams, and you can see in this picture we've got 1 dot for sodium, we have 7 dots for chlorine, and that 1 electron is going to be transferred over to the chlorine to give it 8 in its outer shell, making it negatively charged. And when that sodium electron was given over to chlorine, it became positively charged. It looks like it doesn't have any valence electrons, but it really does, and thus we get this final product on the right-hand side. Let's try an example of showing the transfer of electrons in potassium chloride. We'll start off with potassium, which has 1 valence electron, and we're going to add that to chlorine, which has 7 valence electrons. And we know that potassium is going to give up its 1 electron to chlorine. And so I'm going to keep chlorine in its same position. And I'm going to drop potassium down here just because it's a logical place, almost like a puzzle, to show that that single electron of potassium's valence shell fits nicely into that octet of chlorine. With that transfer, we get a negative and a positive, and basically this comes out to KCl. Let's try another example. This time we're going to use barium fluoride, and we're going to realize that the transfer from one atom to another doesn't result in full outer shells, so we will need to add more atoms. We're going to start off with barium. Barium's in group 2A, so it's got 2 valence electrons, and we're going to add that to fluorine that has the 7 valence electrons. And we know that barium wants to lose 2 electrons, so it's going to give up one of its electrons to fluorine. It has to give up that second electron as well, which means I'm going to need another fluorine available in order to take that electron. Notice how I strategically placed my fluorine's 7 valence electrons around fluorine a little differently. And now we can see that this guy can go right here. And when I rewrite this, I'm going to see barium. And I'm going to put my dot here and here. And I'm just going to go ahead and once again strategically place my fluorines around each barium. And you can see there's the octet, and the octet is giving me the minus charges, giving barium that +2 charge, and that's forming us barium fluoride. The second type of bonding is covalent bonding, and this will occur between 2 nonmetals that are sharing electrons. We have 2 different types of covalent bonding. We have nonpolar covalent bonds, which will exist basically between 2 identical nonmetals that are sharing electrons evenly, and the polar covalent bond, which is between 2 different nonmetals that are sharing electrons unevenly. By taking a look at the Lewis dot diagram that you see on the top, you can see that both chlorine atoms have 7 valence electrons in their outer shell. They both want 8. In order for 2 things to gain, they're going to need to share. And so what happens is they will share this pair of electrons in between. You can see it here as well. And that's going to form the bond between the 2 chlorine. And that would be an example of the diatomic element chlorine. For the bottom picture, you can see that there is 1 valence electron for hydrogen and 7 for the fluorine. Those are being added together. And since hydrogen is one of those atoms that follows the duet rule, we know that it only wants to acquire 1 more. Fluorine also wants to acquire, so they both want to gain 1. And so once again, they're going to kind of share these electrons. Notice how I rearranged the fluorine's 7 valence electrons to kind of fit that hydrogen in like a puzzle piece so that we can see the sharing of electrons being represented by the bond. It's kind of what it looks like right there. And this is for the molecule HF, hydrogen fluoride. The last type of bonding is metallic bonding. And metallic bonding is unique in the sense that we're not looking at different elements coming together. We're looking at just metal atoms that are collectively held together by a pull or a sea of electrons that are being shared together. The electrons move throughout the structure. That's why we call it a sea of electrons. They're able to move throughout. They're not being held by one particular atom. They have the freedom to extend throughout the entire medium of that metal. They're almost like a network. Here's a nice picture of maybe, say, the calcium piece of metal or an aluminum piece of metal. And the pluses are representing the nuclei of each atom. And then you can kind of see the red valence electrons are kind of scattered throughout. And once again, they are able to move. Their movement not only allows metals to conduct electricity really well, but they also help in the shaping of metals as well. We know metals can have great formability, the ability to be malleable and ductile, and that's because of that movement of the electrons.